All right. Hi, everyone. So I'm Tom. I work at the Science and Technologies Facilities Council. We're a UK government-funded organization that supports large-scale science, so big particle physics experiments, astronomy, all types of science. And this is going to be a bit of a look back into one of the clusters that we've been running for nearly 9 years now, to support LHC science in Geneva. Right, yeah. So this cluster, as I say, it supports the LHC experiments. It provides most of the UK's capability for LHC science. And it's co-located with an HTC cluster, and together it's used for the simulation, reconstruction, and analysis of particle collisions in the LHC detectors. This type of science requires a huge amount of what we call online disk storage, and so that's why it's a really big Ceph cluster. It's over 300 individual storage nodes, over 6,200 OSDs, I think, and 110 petabytes of raw capacity. This cluster started life as a dual cluster. It's now Quincy. It's gone through a number of Ceph version upgrades. Some of the data pools are still the original data pools from 2017, and there's 70 petabytes of stored data on the cluster. As you can see, it's doing a fair amount of stuff all the time, anywhere between 20 gigabytes and 100 gigabytes a second of read traffic to the HTC cluster, about a petabyte of data being read off a day. And it's been doing this for about 8 years, or 9 years. So what does it take to do that? It's not very interesting. It looks like many other Ceph clusters, just slightly larger. I think the one note here is the performance is definitely a byproduct of the fact we need 100 petabytes nearly 100 petabytes of online storage. This is about as cheap as you can do, or about as cheap as we're willing to do Ceph storage. We go out to tender every year to try and get good value for money, which means we end up with a mixture of hardware from a mixture of vendors. Mostly these things, there's nothing particularly novel about the hardware. We're getting a new generation every year, decommissioning old generations, and it's sort of a rolling Ceph cluster that moves around our data center as some sort of weird blob of storage. I don't think we're meant to call it that, actually. Right. I'm doing okay for time. So I sort of promised some like general guidance. There isn't really, there's no like pearls of wisdom here. It's a Ceph cluster. The standard community guidance holds. There's a few things that I think are slightly more interesting, or you need to pay more attention to when your clusters grow. I've just tried to distill some of those. So I think the first one, which is something that, and again, all of these are from lessons learned. These weren't things we decided to do. These are things that came up and bit us, and then we're like, oh, we should probably do that differently. Disk hygiene is always important. Ceph is really, really good at running with unreliable hardware underneath, storage nodes disappearing, disks disappearing, and that means you can sort of not worry too much about what's going on. This will eventually be to your detriment. So making sure you're keeping on top of why OSDs are crashing, making sure they can't endlessly crash loop, being quick to redeploy an OSD if you're concerned it's doing something weird, replace OSDs, and if something is weird, remove it. Don't leave it in and wait for it to ruin the cluster in some new and exciting way. Number two, this is slightly nebulous, and again, this is just something we've had to learn over the years. Make sure you can keep track of what should actually be in your Ceph cluster. As I say, Ceph is really good about keeping track of something that you can run a storage technology on, or run a storage layer on top of, making sure you actually know what storage nodes should be in your cluster, how many disks each storage node should have, things like that. It's really useful to have a layer sitting on top of Ceph that makes sense for your environment. That means that you can easily identify where your inconsistencies are, and those sorts of things. And then the final one, this one's a bit more specific to larger clusters, but as your cluster starts to grow, you will have more OSD state changes, the OSD maps will be larger. You need to make sure you're keeping track of how many OSD maps the cluster is having to hold on to, how quickly you're churning through them, and making sure you're minimizing that churn and giving the cluster time to have a calm period to allow it to trim maps. This is something that we don't think about on our smaller clusters. They just kind of do it themselves, but for our larger cluster, we definitely have to think about making sure scrub schedules and balancer schedules have like engineered stops to allow the cluster to chill out for a bit. Right. So this is, I'm going to try and, I've got two slides on sort of what I've called scaling limits. These aren't limits. They're not hard limits. These are just things that we have run into on this cluster as it's grown over the years. None of these are showstoppers. I think they're just kind of interesting things. And this is related to OSD map creation again. On this cluster with 6,000 OSDs, OSD map creation is the thing that has started to take or be the performance limit we've started to observe. It takes about 2 seconds to make an OSD map on this cluster, and there are many things that will need a new OSD map. There are also many things you're doing if you're interacting with a Ceph cluster as an operator that need to wait for a new OSD map to be created or need to wait for an existing OSD map creation process to finish. So the general cluster lagginess of commands, this is the main cause. The interesting note, which was again found out from an operational piece of excitement we had, if your monitor quorum duration, so the amount of time the monitors are happy to have a quorum before they check they're all there again, if your OSD map takes longer to create than that, your lead monitor will start creating the OSD map and then fall out of the quorum, and then you will never have a Ceph cluster again. And that's really exciting. Obviously, once you know what's happening, you just allocate more resources to the leader monitor so it can create the OSD map within that interval, and you increase the interval. But yeah, it's slightly exciting when there's a big state change on the cluster and then suddenly the monitors stop responding. But yes. Cool. Finally, the other scaling limit, which I think is useful to know about, but it's very simple to solve, is just there is actually a limit of the sum of crush weights in the crush map. At the default scaling of one unitless crush weight is 1 terabyte. You will hit this limit at about 70 petabytes of storage. It's quite exciting when you hit it. If you don't know you're going to hit it, but if you know what you're looking for, you just rescale all your crush weights. We picked 1 = 1 petabytes because, I don't know, we thought there needed to be that much room for growth. But yeah, that's just something to look out for. If you know you're going to be building a really big cluster, maybe do this from the get-go so you don't have to do it on a production cluster. And yeah, finally, another note on that. There may be things that you're using that are trying to add OSDs back in at the original crush weight scaling. If you let them do that, things will get very exciting because you'll add a 20 petabyte OSD and every placement group will move, and then you'll run into the problem on the previous slide. Yeah. Cool.